Welcome to the Explainer. Today, we're basically upgrading your mental model from a beginner AI engineer to an absolute senior level. We're going to master LangChain and LangGraph for production. So if you've been building simple chatbots and you're ready to learn how the pros design resilient, stateful agents, the kind that won't hallucinate your company right into a PR disaster, you are in the exact right place.
Okay, here's our roadmap for acing that advanced AI system design interview. We'll be hitting the AI orchestration layer, the risks of dynamic agents, mastering LangGraph and state, memory versus checkpointing, and finally, production system design.
All right, let's dive straight into Section 1, the AI orchestration layer.
So, what's the actual difference between LCL, which is the LangChain expression language, and LangGraph? This is a classic interview question, and it literally separates the novices from the seasoned engineers. It's not just some minor syntax difference, it's a fundamental architectural choice that completely dictates how your application is going to behave.
Think of LCEL like a factory assembly line. It's for predictable, linear workflows. The prompt goes in, the model thinks, the parser outputs, and boom, you're done. LangGraph, though, that steps in for the heavy lifting. When your workflow is complex, cyclic, or stateful, like if you need to loop back, pause for a human, or conditionally route based on what just happened, you absolutely need LangGraph.
Now, if you want a truly senior-level answer in an interview, use this exact framing. I use LangChain for composition and LangGraph for orchestration. Saying it like that shows you totally understand that one framework connects individual components, while the other acts as the brain, controlling the execution and the entire lifecycle of the agent.
Moving right along to Section 2, the risks of dynamic agents.
An agent sounds incredibly cool, right? It's an LLM-driven decision loop where the model dynamically figures out actions on the fly instead of following hard-coded steps. But here's the catch. That exact same unstructured flexibility is what makes them wildly dangerous in a real production environment.
Seriously, an unchecked agent can wreak absolute havoc. You're looking at infinite loops where the agent just gets confused and thinks in circles forever. You've got hallucinated tool arguments where it just invents parameters out of thin air. And my personal favorite nightmare? Cost explosion. Letting an unconstrained loop spam an expensive model is a fantastic way to bankrupt your token budget overnight.
So how do we fix this? Production-grade systems use strict, layered controls. You don't just throw in casual helper functions. You need strict schema validation to instantly reject weird arguments. You need execution budgets to cap your token spend. And crucially, you need a human in the loop. Basically, anything destructive, like deleting a record or issuing a refund, requires manual approval, no exceptions.
Which brings us perfectly to Section 3, mastering LangGraph and state.
The real secret to taming those rogue agents is the state machine. By implementing a state machine, we take that open-ended, highly risky agent loop and we wrap it up in a safe, controllable framework. You define the exact transitions, which means you know exactly what state your application is in at any given millisecond.
So instead of just a basic linear chain, LangGraph uses nodes to perform distinct steps, like retrieving a document or calling a tool. And it uses edges to act like traffic cops, dictating exactly where the data goes next. The nodes do the actual work and the edges control the flow.
And the type of edge you use, it matters a ton. A simple edge is just a straight line. It moves unconditionally to the next node. But conditional edges? That is where LangGraph flexes its muscles. If a tool fails, does the graph try again, or does it escalate to a human? You encode all of that crucial business logic and recovery routing directly into the graph using conditional edges.
Now, all of those edges rely completely on state. State is the shared data structure passed around that holds everything. User input, tool results, error counters, you name it. It makes the runtime workflow totally explicit instead of just implicitly hiding everything inside some giant, messy prompt. Because it's structured, your code can confidently look at the state and decide where to go next.
All right, moving to Section 4, memory versus checkpointing.
This is a massive point of confusion in interviews, so you absolutely need to nail this distinction. Memory is knowledge persistence, is the facts and preferences that span across multiple sessions. Checkpointing, on the other hand, is runtime persistence. It's literally just a snapshot of your graph at a specific moment so you can recover from a failure or wait for a human to click approve. A checkpoint is not long-term memory. And because memory actually persists facts, a senior engineer knows you can't just wing it. You need strict governance. We're talking explicit write policies,
PII reduction, so you aren't accidentally hoarding social security numbers, expiration dates, and source attribution to track exactly where the agent even learned a specific fact.
Keep this rule in your back pocket. Bad memory design stores everything forever. Good memory design only stores useful, safe, durable facts. Don't let your agent blindly dump massive chat histories into a database until the end of time. It needs to carefully curate what is actually useful for the long haul.
And that brings us to our final section, production system design.
If an interviewer asks you to design a support agent, they fully expect you to rigorously track 4 critical metric groups. Quality, like how grounded the answers are. Reliability, tracking your timeout rates. Cost and latency, because obviously tokens aren't free. And safety metrics to catch prompt injections. An unmonitored agent is just a massive liability.
Let's say you're fighting hallucination. Don't just prompt the LLM to be truthful. That really doesn't work. You have to build a multi-layered defense into the architecture. Use hybrid search at the retrieval layer. Force the prompt to rely on context. Actually build a verification node in your graph layer to double-check the LLM's work. And at the end, mandate citations. Here is your absolute mic drop moment for an interview. My design principle is to keep business-critical control outside the LLM. Stating this proves to an engineering manager that you prioritize real safety, testability, and observability. You aren't just crossing your fingers, hoping the AI behaves, you're engineering the environment to guarantee it.
Always remember this. The LLM does not own the whole system. It reasons, but the graph controls execution. The language model is an incredibly powerful reasoning engine, for sure, but it is not the boss. The LangGraph orchestration has to be the ultimate authority.
So, armed with this senior-level mindset, I want to leave you with a final thought for your next big project or your next interview. If the LLM doesn't control execution, how will you design your next graph to keep it safely bounded? Think really carefully about the nodes, those conditional edges, and the exact state structures you'll use. Thanks for hanging out with me for this explainer. I really hope this helps you build smarter, safer systems. Keep learning, and I'll see you in the next one.